Today we are going to talk about the role of calculus of variations in mechanics. We had discussed that at the beginning of this lecture, but now that we have discussed calculus of variations in detail, that is with constraints and then two types of constraints, functional constraints, function type constraints or global and local constraints, and the general variation. Now let us revisit that in the context of beams. First let us look at something that we had discussed earlier about mechanics seen in three different ways. So, if you look at mechanics and calculus of variations, we have three views of mechanics. So, we have first one, let us say three views of mechanics. We are discussing both statics and dynamics, right. In the case of statics, if you just want to use force balance, that is perfectly all right. Alternatively, one can use principle of virtual work. That, and then if you want to find another alternative, that is a minimum potential energy principle, right. So, this leads us to calculus of variations. If we start from calculus of variations where we want to minimize potential energy, where the variable is the deformation, lot of possible deformations, only one will be chosen which minimizes the potential energy, that is the one, that is the static equilibrium solution. If you start from here, then you can move up and we will get principle of virtual work, which is nothing but the weak form of differential equation, which you get from the weak form you can get the strong form, that becomes force balance. Okay. So, if you start from minimum potential energy principle, you can get what we call weak form of the differential equation or force balance, which we call strong form of the differential equation. So, dE when I write, I mean differential equation that governs the static equilibrium condition. If you start from force balance, you can actually come here, which we also is known by several names. Galerkin method, a mathematical method, gives you the weak form, and from there you can actually come to a minimization principle under certain conditions, which we will be discussing later. So, if you start over here, you can come back, that is if you start here you can come back to this and you can come back to this, or if you start here you can go back to this and go back to this, or if you start from the weak form or principle of virtual work, you can get the strong form or you can get this also. So, all three of these are equivalent. So, if you know one, you can get the other two. So, you can believe in any one of these and we will be fine. This is all for statics. Similar thing exists for dynamics also. So, if you start from Newton's second law, everybody knows this, F equal to ma, that is equivalent to D'Alembert principle, which is like a weak form of that, and from there you can come to something called Hamilton's principle, right. Or you can start here and go there, and from here you go there, or from this you can go to this or that. These are three equivalent principles in mechanics, and calculus of variations in a way ties all of them together, because when you take, let us say, statics, minimum potential energy principle, from that you can get the weak form or the principle of virtual work, from there we can get the force balance, which I intend to show using the example of a beam that you would have learned in your mechanics of materials course. So, where we have where is this? Can you just come? I opened this, but I do not see the pen thing.
Here we have to select top.
Oh, this is not there. Yeah, I got confused. Yeah. Okay, let us take the beam problem. Let us take the beam problem. Okay. In fact, let us not worry about constant cross section beam. We can take a variable cross section beam. I will only draw the neutral axis, okay. And as far as the cross section is concerned, let us actually take intentionally a variable one, which in a normal mechanics of materials class you would not take, right. So, here we have at every point there is a cross section, okay, whatever shape, whatever size parameter there may be there, let us say that is A of x, and our x starts here, this is our x is equal to 0 here, x equal to L, and A of x is a function, right. If we take up the beam problem, let us start from minimizing the potential energy. So, if I say minimize the potential energy of this beam, which has let us say some load acting on it, okay. So, if I say a line diagram now, so I will just write the beam, even though it has cross section, I will just show this, that the force is acting on it in some fashion. Let us call it Q of x. So, everywhere force acting as per the function Q of x, and the boundary conditions do not matter. I am just showing a cantilever beam, but they will come out of calculus of variations calculation that we are going to do. If we have this, so we want to minimize this potential energy with respect to W of x. W of x is that this beam is going to deform under the load, and this displacement is Wx, okay. That is a transverse displacement. So, when a beam has a loading, it can deform in many other ways, but it is going to take a particular deformation, what we can call let us say W star of x. That is a solution of this problem, minimize the potential energy problem. No constraints here, just minimize the potential of the beam with respect to Wx. Now, let us say what this potential energy for a beam is. In general, potential energy is strain energy plus work potential, as we had already stated once. Strain energy is this SE, and work potential we can actually call it work potential energy. If you just want to say that it is energy, so I also want to see energy explicitly stated there, it is work potential energy, that is potential energy due to the work done by the external force, that is exactly what it is, but it is negative of the work done by external forces. Here Q of x is the external force on the beam. There are a lot of internal forces, we do not consider that, it is only the external forces, okay. Why is it negative? Negative because in thermodynamic thinking, work done on the system is negative, that is how we put this as negative energy, negative potential energy the external forces, whereas strain energy is the energy stored in the structure. So, this strain energy we can write are the cumulative for the overall elastic body. The beam is an elastic body here. So, there we integrate over the volume, okay. What do we integrate? We integrate strain energy density, strain energy density, which is simply strain energy per unit volume. This strain energy density is defined as the area under the stress strain curve, okay. If you write sigma versus epsilon, area under the curve for the linear analysis, which is what we are discussing now, it will simply be sigma epsilon by 2, okay. So, we have strain energy density here, we want to integrate the entire volume. So, then we ask the question, what is the relation between stress and strain? So, we have sigma for a beam, there is only one stress sigma and there is one stress one strain epsilon, normal stress and normal strain, they are related by E, which is Young's modulus, which is material property here. Okay. Now, if we substitute over there for our strain energy, okay, our strain energy here. Now, this strain energy is integral V coming back from here, sigma if I substitute it will become E times epsilon, another epsilon is there, square by 2 over the volume. Okay. Now, looking at the beam at any given positions, if I take let us say this one, there is some cross section area here and a length dx. Let us say I want to cover the entire volume. So, I take a dx, a slice of the beam, and that if I look from this side it is going to be some cross section, right. In this cross section I can take a little one, something like that, little square, call it dA. So, I am splitting the dV, that is the overall volume that I have this little disc, okay, of the thickness dx, okay, this is dx, that is dx, and then dA. I will have a little thing that we will have to integrate over the area first and then the length also. So, if I take that, I can split this as two integrals, one over the area, another one over the length, so that I can cover the entire beam. Okay. If I want to cover the disc that we just drew, we have to integrate over the area. So, that is this disc we have to integrate over this entire area here, and then we have to integrate from x equal to 0 to x equal to L, then we will cover the entire volume of the beam. So, I put 0 to L and A over the area of the cross section, and then we have E epsilon square by 2 dA and then dx. So, basically dV is split into dA and dx, right. Next thing we recall is what is epsilon, that is a strain, normal strain in the beam, which if you recall from mechanics of materials is given by minus y by rho. Y is something that is measured from the neutral plane to the point under consideration, that is I have taken that dA at certain height. If this is the point through which neutral axis goes, let us say I put this in yellow, right. So, over here is neutral axis, the dA is at a certain height, okay. Maybe the other color is better. So, this is y, you know that, but if I take a point over here from the neutral axis to this, right, that little distance is y. As the beam bends, the way we take our convention to for the beam that is straight like this, deforming like this is considered positive. So, if I neutral axis is the center like this, if I take a point above the neutral axis, that would be here, these things will be under compression, and hence strain will be negative, and that is why we have the minus sign over here. Okay. Another thing we know is note that strain is linearly proportional to distance from the neutral axis, that is why it is minus y by rho, and y that is linear for the strain. Other thing we know is that 1 by rho is the w function that we have, the second prime of it, that is d square w by dx square divided by 1 plus w prime square raised to 3 over 2. Okay. But in cases where w prime is small, that is the slope of the beam that is deforming is not significant, we can neglect that. So, we can neglect this compared to 1 that we are adding to. So, this can be approximated as simply w double prime. Okay. If I do that, this is going to become minus y into w double prime, because 1 over rho is approximated as w double prime, right. So, now if we come back to this, we can write this as 0 to L E epsilon is now square y square w double prime square by 2 dA dx. Okay. Now, we will rearrange a few things to take out the things that do not depend on that do not change on the area, which if we assume E is, number 2 is of course, and then the w double prime square also, because that is something that does not change on the area of cross section, because a one dimensional model, the beam theory one dimensional model of the 3 dimensional solid beam, we just have a neutral axis. So, if you take a slice at a particular value of x, the w there is the same, because if you recall the way we do this here, we just show this, we are not saying what exactly happens to the beam as its width is there. So, across the width we do not say anything, all of that deforms like this, we are only worried about the neutral axis deformation, right. So, that can be taken out. What is left here, we will have y square dA over, so here also dA is there, so I should put over the area carrying there. So, this is over the area of cross section, okay, and then we have dx. Now, if you see this quantity that we have is what we denote as I, or second moment of area, second moment of area of the cross section. Sometimes it is called moment of inertia, that is actually incorrect, because there is no mass associated with this here, it is purely a geometric property. So, calling it second moment of area is appropriate. So, if you had learnt it as inertia, change it to call it second moment of area and not inertia. Okay. So, this gives us 0 to L E, I will call this I now, w double prime square by 2 dx. Okay. All this we are discussing again to potential energy, we have written what strain energy is, work potential, both of that we do. So, we get, so I would now write minimize potential energy, which is strain energy plus work potential. Strain energy as we have just derived 0 to L E I w double prime square by 2 dx, that is strain energy plus work potential. So, let us write work potential in blue color, that is negative of the work done by external force. External force is here Q, and then it is being acted upon through a distance W, that is a transverse displacement. So, this will be the work potential. This also goes from 0 to L dx, because Q of x is acting, W of x is the consequent deformation product of these two. So, together we can write it as one functional. So, we have problem minimization with respect to W of x of potential energy, which we can write as 0 to L E I W double prime square by 2 minus Q W dx. Now, we got a calculus of variation problem, or rather minimization of potential energy, that is the principle. So, here what do we do? First thing we do is to take the variation of potential energy, that is our functional here with respect to W equated to 0. If we do that, what we get is that 0 to L, I want to take variation. So, that will become E I W double prime, this square and half will go away. So, that 2 here and the 2 that you get, because W double prime square, this 2 will get cancelled into delta W double prime minus Q, and then we are taking variation. So, delta W will be there, this whole thing dx should be equal to 0. Okay. Now, this particular thing, if you see, if I just write it in a slightly different form, I will say 0 to L E I W double prime delta W double prime equal to, because the minus is there. I take this to the other side, q into delta w dx, okay, because that is equal to 0. I have taken this term to the other side, right. So, now we see what this delta w is for us from the calculus of variation. It is the variation of w of x. Delta w of x is a variation of w x, meaning if the beam has deformed here, we are perturbing around that perturbation, little perturbation that we have here, that is our delta w of x, right. But now we can also think of this as virtual displacement, w of x is the real displacement, then delta w of x is a virtual displacement. So, what is this quantity here? This quantity here, if delta w is virtual displacement, this is the, because q of x is external force, this is external virtual work. Okay. So, what we are saying is that somebody says that this particular thing for a straight beam, if this is the equilibrium deformation under some loading q of x, okay, we want to verify, is it really? We go back to principle of minimum potential energy and imagine a virtual displacement as if it is perturbed. When it is perturbed, to first order it should be equal to 0. That is exactly what our variation potential energy with respect to W says. So, external work, and this portion is actually internal virtual work, internal virtual work. Okay. So, these two being equal to is nothing but the principle of virtual work, principle of virtual work. That is, if you have a structure, if you believe that a particular deformation is an equilibrium deformation, then if you imagine a virtual displacement, it is a virtual not real, then the imaginary virtual work due to external forces is equal to the internal virtual work, because this is nothing but strain, right. That is what we had just written for a beam, that our epsilon is proportional to W double prime here. So, the epsilon is W double prime. Y is there, of course, for a beam across a cross section, strain varies linearly, that is why Y is there, otherwise it is proportional to delta double prime. So, that is like real strain, this is real strain, and delta W double prime is the virtual strain. Okay. So, if you imagine delta W virtual displacement, there will be strain. So, real strain, real stress, and then we have of course this E here, because stress and strain, if you multiply you get the internal virtual work. Basically force and stress are equivalent, displacement and strain are equivalent. If force times displacement has units of energy, stress times strain also units of energy. So, this is the work or energy, both have units of joules, right. So, internal virtual work, external virtual work, that is what we got. So, this one tells us that from principle of minimum potential energy we can derive the principle of virtual work. If you go one step further, which was our integration by parts. So, if I start from principle of virtual work 0 to L E I W double prime delta W double prime minus, I am bringing it to the left side again, 0 to L Q delta W, well I have to write dx, right. So, we should not forget that. Let me, whenever I have integration with respect to what, right. So, integration with respect to x here. So, if we have this here, so dx equal to 0. Now, we need to, because delta W is the one that is arbitrary. So, we have to get rid of this, meaning we have to do integration by parts, we have to do twice, and that gives us the boundary conditions as we had seen earlier, right. So, if I do integration by parts once, then I will get the first function, that is this thing, integral a second function, that delta W prime, that is that. minus derivative of first function d by dx of E I prime. So, I have written d by dx, I do not need to write prime here, okay, d by dx of that integral of the second function dx, and this stays as it is, that is q delta w dx equal to 0. Now, we need to get rid of this by doing another integration by parts. So, when I do that, so I will have the same thing here, E I w double prime times delta w prime at 0 to L minus here again the first function if I take, that is d by dx of E I w double prime, okay, times integral of the second function delta w 0 to L minus of minus plus minus of the minus thing of the integral of the derivative of the first function, that will become second derivative d square by dx square E I w double prime integral second function, that will be delta w dx minus 0 to L q delta w dx equal to 0. Now, we get the boundary conditions and the differential equation. So, for differential equation we take this and this, I will write it in black, 0 to L d square by dx square of E I w double prime, okay, minus q, this whole thing multiplied by delta w dx, plus we have the boundary condition which I will write in blue, this one and that one. So, that will be E I w double prime delta w prime, that is a virtual strain or variations strain, minus d by dx of E I w times delta w at 0 to L, all of them are 0. So, individually we say this is equal to 0, this is equal to 0 and this is equal to 0, right. Unless somehow delta w prime and delta w are dependent on each other, you can make up problems of that kind, then you have to put them together and say it is 0, otherwise you say individually things are 0, okay. So, if you make them individually 0 and the fundamental lemma of calculus of variation say that this is arbitrary, for if you make that individually 0, which we have to here for boundary conditions and differential equation part, that is arbitrary. The fundamental lemma tells us that what multiplies, that is this thing should be equal to 0. If I write E I w double prime and this d square by dx square, I will just put it as 2 primes, okay, minus q equal to 0. This is what we get. So, if I were to be uniform, that is it does not vary with x, then that will become E I 4 divided w is equal to q or minus q equal to 0. That is what you have learnt in mechanics of materials when you discussed, when you learnt beam theory, but this is more general, this is for variable cross section. And then we have these two are the boundary conditions, okay, these are the boundary conditions, because we have a fourth order differential equation. So, we need enough boundary condition to solve for the 4 constants that are there. W, let us say E and I are not dependent on x, then you get a fourth derivative of w. When you integrate it, you need 4 constants. We have 2 sets of boundary conditions at 0 and L and 0 and L. So, you get 4 of those to solve for these boundary conditions. So, now we can see the weak form gives rise to strong form. This is strong form. Why is it strong form? Not strong worm, it is strong form. Strong form. Why is it strong form? Because W here needs to be differentiable 4 times, whereas if you go back to our principle of virtual work, here W needs to be differentiated only 2 times. That is why it is called weak form or the principle of virtual work, whereas the other one is strong form. Okay. So, what we see now with the example of a beam, that we can use principle of minimum potential energy, go back to weak form or the principle of virtual work. From there we can go to force balance or our differential equation along with the boundary conditions. So, whatever boundary conditions are there, whether W is specified or slope is specified, we can go back to these conditions and write out our boundary conditions, Dirichlet, essential, or Neumann or natural. So, when W is not specified, this thing is not 0. So, E I W triple prime should be 0 or d by dx of E I W double prime should be 0, where I can be a function of x as we have taken. And this equation is very important for us, because now when we want to design a beam, we actually make W of x as a state variable and look at I, the cross section as a function of x is what we have taken. That is what we design, that becomes the design variable, and this equation that we have becomes the governing equation for the state variable, which is W of x, governing equation for W. W of x cannot be anything, it has to obey this equation, because that is what controls the static. Similarly, for dynamics, if you do, the Hamilton's principle will give you the dynamic equation, which we will discuss in a later lecture when we look at the calculus of variations role in dynamics. Thank you.